Hello, everyone. How do you do? So this talk is titled The Architecture of the P4-16 Compiler. And actually, there turns out to be many P4-16 compilers, but I'll talk about one of them. And first of all, let me just remind you briefly about P4-16. So P4-16 is the newest version of the P4 language, which was officially finalized yesterday, but has been under work for more than 2 years now. So it's not just a sudden creation. It was polished through a long process. So the specification is available on GitHub. Please download it and take a look and try to find holes in it. Now, we actually also, I don't believe you can write a specification without building an implementation. So the specification and the reference implementation for the specifications were built simultaneously. We actually started by writing a specification, but then we started implementing it as soon as we finished writing it, and then we found lots of holes, and this process continued. And the compiler tracks the specification pretty closely, although it's a little bit behind, and some features are not implemented. So what I'm going to talk about is this reference implementation, which makes sure that the spec actually makes sense. It's implementable. Now, the reference implementation compiler that I'll describe can also compile programs written in the old version of the language, P4-14. Because P4-16 is syntactically incompatible with P4-14. And if you don't provide a migration path, then a language becomes much less useful. So P4-16 should be at least as rich as P4-14. Everything you can write in P4-14, you should be able to write in P4-16. And as a proof, the compiler will actually happily ingest your P4-14 program and generate an equivalent P4-16 program for it. And as far as we've tested, they should behave the same. But you might find bugs in that too. And then the good news is that everything is free and open source. It's an Apache 2 license. And as you see, it has quite a vibrant community. So there's, hundreds of commits, tens of contributors. There's lots of issues filed. That's not necessarily good, but it shows that people care. All right. So now, why do we want a new compiler? What's wrong with the old compiler? Well, it depends on your goals. And then these are the goals we set for building the new compiler. And we think it would have been much harder to meet some of those goals with the old code base. So first of all, we want to support current and future versions of the P4 programming language. As you see, the new programming language, P4-16, has a different syntax. Also, we want the compiler to support multiple backends. So we want to be able to compile for ASICs, NICs, FPGAs, software switches, and you name it. That's actually a very ambitious goal, because these targets are very, very different in capabilities. Also, we want to provide enough support in the compiler to build other tools like debuggers, IDEs, control planes. For the control plane, I think we did a pretty good job. The other ones, they still have to be done, at least based on this new compiler framework. Then we really think that P4 is only useful if people can use it freely and easily. So the compiler front end has to be open source, because we want people to use this front end ideally and build only their custom backends. And we want the compiler to be extensible, because all these targets have different capabilities and maybe other targets that I don't even know about. So we want people to be able to add new passes and transformations easily. And then we also wanted to do good software engineering. So we try to use in the compiler all sorts of techniques that people who write compilers have developed over the years, like an immutable intermediate representation, which I'll call IR in the rest of the talk. It's based on something called the visitor pattern. Don't worry too much about it. I'll talk about it briefly. It uses strong type checking to make it much harder to write incorrect compiler passes. And we also wanted to have comprehensive testing. Now, I think a compiler needs at least 10,000 tests in order to be declared healthy. This one has less than 1,000 in the public repository, so we're still far away from comprehensive, but we are trying. And since everything is open source, we welcome your contributions to any of those steps. So the reference implementation looks a bit like this. So it has two parsers. One parses the old P4-14 grammar, and the other parser parses the P4-16 grammar. Now, the P4-14 grammar is then converted to a P4-16 representation, and from that point on, everything in the compiler uses the same representation. So everything you do in the front end after this conversion step applies to whatever program you ingested. So if you write a nice optimization which makes your code more efficient, hopefully you can apply it to all your programs, no matter which language they were written in. And then we have a pluggable system in which you can write midends and backends custom to your architecture. Now, in the public repository, we provide 3 public backends. One is just for testing, so I didn't put it on this slide. But one of them generates C code, which can be compiled further to eBPF and then run in the Linux kernel. And another one generates a JSON representation of the program, which can be ingested by the behavioral model simulator, which is the standard way you can test P4 programs today. But we hope that you'll fill the dotted box yourself with your own backend. And one purpose of this talk is to convince you that shouldn't be that onerous. All right, so as I said, the compilers that are written for P4 using this framework are expected to have three pieces. The front end is completely target independent. So the only thing it does, it validates your program, it type checks your program, and it also makes clear the program semantics. Although P4 is a very simple language, turns out there's a lot of interesting corner cases you have to worry about. And the front end tries to make sure that you don't have to worry about them because it translates them into simpler cases which are more homogeneous. And the front end today consists in about 25 passes, distinct passes. Some passes are run repeatedly. So in all, I think there's maybe 40 passes, but there's 20 distinct transformations that are done on the program. Some of them are very, very small. Then everything in the compiler is represented using the same intermediate representation, and I'll talk about it later. And then the midend comes. Now, midend I'll describe briefly. We also have about 25 distinct passes that you can use in the midend, but we expect that this number will grow because many passes in the midend will be target specific. So if you have a custom target, you should probably slot your stuff there. And then the backend, you can write your own backend, and you can use our IR, you can create your own IR, you can extend the IR we provide. So to make it clearer, this is actually how the passes are organized. So the front end is a library. So it's a service that we provide to you. If you want to use this compiler, we'll give you this service for free. And the order of passes is fixed. You can make, since the source is available, you can change that, but you're not supposed to change the front end. Now, the midend, what we do is we provide you a library of many passes that we wrote, and then you can just mix and match from those. Some of these passes have a fixed behavior, but some other passes may be parameterized with the policies, and these policies could be a function of your backend. Just to give you an example, for example, P4-16 has an enum data type, like the C enum. It's just symbolically named constants. And then maybe sometimes you want to convert those enums into integers or whatever representation your target uses. So you supply a policy which says, oh, I want my enums all to be 32-bit integers. And then you call our pass, which converts enums to integers. So the policy tells you how to do it, but the pass does all the work for you. So this is the kind of stuff we expect to have in the midend. Passes that are mostly target independent, but sometimes call simple policies which are target dependent. And in the backend, you're on your own. You have to write your own stuff. But you have at least 2 sample backends to look at. All right. Now, there's a common infrastructure for all the passes, front-end, mid-end, and backend. And we use the same intermediate representation, the same base classes for visitors. The visitors as the guys that transform the EIR. And we use a lot of common library utilities. You have our own collections, our own strings, because everything is written in C++, and whenever you write a C++ project, you implement all your own libraries. That's how C++ works. So this is C++ 11, and actually it's garbage collected C++, which is actually very nice, surprisingly nice. It works very, very well, and you never have to delete a pointer, and that actually makes many, many classes of bugs disappear automatically. So we don't want to worry about the correctness, manipulating the data structures correctly. We want to worry only about implementing the correct P4 transformation. So we made it as easy as possible to write the compiler code itself. So it's almost as easy as Java, I'm claiming, because you never use, for example, smart pointers. Everything is just a raw pointer. And then we have this clean separation between front-end, mid-ends, and back-ends, and we allow you to change mid-ends and back-ends. And we can even allow you to extend the IR. As you see, the IR is defined in its own little custom language. And we can also save the IR to files and read it back in. So you could technically transport the IR between machines and run your backend someplace else. So the IR actually is essentially a data structure which represents your program. And it's designed to be immutable. So once you build an IR object, you cannot change it anymore, which makes it easy to share. So each pass can produce an IR object, and you're pretty sure that if you have a handle to an IR object, nobody can trample over it. See, this is enforced by the C++ type system. And this actually makes it even possible to write a multi-threaded compiler in which you fork multiple threads to try different optimizations simultaneously, and you're guaranteed that the threads cannot trample each other's data structures if they are the IR. You can have other side data structures, but the IR is immutable. And everything is strongly typed in the IR. As I'll show you a little brief fragment, each node in this DAG has a type, and the children can only have specific types. And the IR is only manipulated by visitors. And you can, as I said, you can add new IR classes if you want. Now, what is a visitor? This is a quote from the Wikipedia visitor pattern. So it's a software engineering pattern. It can look a little daunting at the first time, but the more you use it, the more you'll appreciate it. It's very nice. So what happens is in a compiler, usually, as you saw, we have 50 passes. So one way you could build the compiler is to have a structure called, whatever, IR class, and then that class could have 50 methods. Each of those methods would be a transformation of the compiler. But it doesn't scale. You can't keep adding methods to your classes. So the way the visitor pattern works is the visitors are separate from your data structure. They are code which manipulates your data structure. The data structure is fixed and only represents the data. All the code that manipulates the data structure is separate. That's the visitor pattern. And just to show you how you can manipulate an IR which is immutable, you actually use copy on write. So what happens, for example, on the left I show you a gray tree. And then let's say some transformation wants to replace a blue subtree with a green subtree. So you want to splice it in. So what you do is you only do some pattern matching in your code. And when you see the blue subtree, what you return is the green subtree. And then the IR framework, the visitor framework, what we'll do, it will splice the new green subtree in. It will also rebuild the whole spine. All the nodes that are used, the orange nodes that are used to reach your blue subtree, they have to be replaced with new nodes. You can't mutate the old nodes. So what you get is a new root which points to a completely different tree. Everything that is gray is actually shared between the old and the new representation. The blue stuff becomes garbage, which is just garbage collected, and then that's how you get a new immutable data structure. So you can keep all of them around if you want forever, or they will be garbage collected if you don't need them. Now, the IR is defined in its own little programming language, which is a very small subset of C++. You could say it's like Java. And this is an example. For example, the assignment statement at the bottom, it shows you how the assignment statement is represented. The assignment statement has two expressions, the left side of the equal sign and the right side of the equal sign. So they are just pointer to other IR nodes, expression left, expression right. So there's a whole class hierarchy, and every P4 construct has a representation in this IR. Now, one decision we made, and I see that I was talking too slowly. I said, this is after lunch. I shouldn't get too quick here, but I'm running out of time. So I'll speed up a little. So one invariant we establish in the compiler is that all the front-end and mid-end passes, the IR is so high level that you can go back to P4. So actually, this is incredibly useful. It makes it much, much easier to debug and test your compiler, because as you go through the compiler, you can always dump back P4 and see how your program looks in the middle of the compilation chain. And we maintain position. And one thing we can do is we can also dump as comments. So we can dump back P4, and as comments, we can dump the IR next to the P4. So for example, whatever is red is a representation, a texture representation of the IR, which is a DAG. And what is black is P4. So we'll just dump the IR next to the P4, which represents the IR. So this is an easy way you can learn the IR. You just write your P4 program, run the compiler, choose a point in the middle, and see how the program looks, both as text and as IR. One thing we built is this V1 model. So P4-16 actually can compile for any target. Now, if you want to compile programs written for P4-14, you have to specify a target, and we built this V1 model. It's a model of the initial P4-14 target. And it provides the backwards compatibility for all P4-14 programs. I said we wanted to test the compiler, and the testing of the compiler takes advantage of some of those features. So we could dump, say, look, this big horizontal box, that's the compiler itself. It's a pipeline of many stages. And you can choose at any point in the pipeline, you can actually dump the IR back as P4. So the way we test the compiler is we dump the IR in 3 specific points today, but we could choose others if you want, and we save the representation, and we vet it. So somebody reads the representation and makes sure that it's correct. And then when we make changes to the compiler, we continue to compare, and if the representation diverges, it means we introduced a bug. So we do this also for the standard error. So sometimes your compiler is supposed to fail. It means it's supposed to reject the program which is incorrect. So we have a lot of negative tests. And for those, we also check that the compiler will continue to give the same errors when you change your compiler structure. Also, because we can generate P4 out of the transformations, we can recompile the generated P4. So that's another form of self-validation. And then finally, we built a very simple testing framework in which if you compile a program for this model that I've shown you, the P4-14 model, we already have a simulator for this model. So what we do is we generate input for the simulator, which happens to be some JSON representation of the P4 program. And then we also have, we save packet traces, input traces and output traces. And we can run the simulator on these traces, and we make sure that the output corresponds to what we expect. And that's very nice because this is end-to-end program testing. So we really know that the output of the compiler has the same semantics on the traces that we supply. All right, so this is my last slide. So what have we learned? I think actually the process works pretty well. So P4-16 is designed to be a simple language. So maybe it doesn't look simple, but if you look at the other languages around, it's actually a really, really simple language. And the libraries are very small at this point. But P4 is designed to work in a very complicated environment. And P4-16 makes this very clear. We allow you to put arbitrary functionality in the environment, queuing, scheduling, cryptography, whatever. Your external blocks can be arbitrarily powerful. So because we don't know what the environment is, we have to allow for flexibility. And we designed P4-16, the language and the compiler, for flexibility. So we must have an extensible compiler if we want to support an environment that we don't even know at this point. And it seems to work. So at this point, I'm aware of 5 backends that were written for this compiler. And these backends target things as diverse as software switches, FPGAs, and ASICs. Now, I won't say they are in tip-top shape, then you can throw any program at them and they will succeed. But they are good enough to test a large variety of programs. And I think that this process of iterating tightly between specification and implementation is crucial. If you make only one of them, you will make significant mistakes. You really have to say what you're going to build, then build it, and then make sure that you build what you said you're going to build. And then this all wouldn't be possible without a great community. So I'm giving this talk here, but this represents the work of many people, and I want to thank you all for your contributions.
Questions for Mihai?
Sure. So the question is whether there are Boolean expression optimization in the front end. There are some. So there's a strength reduction pass, which does some things like that, but it should be fairly easy to add more. So the question is whether there does any dependency analysis. So the P4-16 language actually is much richer. It allows you to do arbitrary assignments in your code. And there is a def use analysis pass which keeps track of what is defined and where it's used. But it might not be sufficient for your needs. Yes? The eBPF output part of the standard compiler, and how deep is it? I noticed one of the first slides had an eBPF output. Oh, so the question is about the eBPF compiler? So I'm not sure I know what your question is about. All right, so there's actually 2 eBPF backends I contributed to. One of them is actually in the same GitHub repository as the main compiler. And there is another one that my company has been working on, which is a superset of the functionality, which is also in a different public GitHub repository. They are both public. But one of them is in the same repository as with the main compiler. And that one is not very well tested, I can say. But yeah, we hope to make it better.
Okay, let's thank Mihai.
Thank you.